You know that feeling when you're staring at a weather map, looking at all those colorful letters, spiky lines, and swooping curves? It kind of looks like a giant, chaotic puzzle, right? But meteorologists look at that exact same raw data and see a perfectly clear story. We interact with the atmosphere literally every single day, yet most of us don't know how to actually read it. Well, today, we're changing that. We're going to crack the code of those surface analysis charts and turn those static symbols into a living, breathing forecast. Welcome to today's Explainer.
All right, here's our game plan for today. First, we'll be decoding pressure centers, then we're tracking frontal boundaries, moving from data to forecasts, and finally, making our very own weather predictions.
Let's jump right into part 1, decoding pressure centers, the absolute foundation of it all.
Before we even think about moving weather systems, we've got to understand the heavyweights, the anchors of the atmosphere. These are the foundational building blocks of our atmospheric decoder ring. High pressure centers, marked by that big blue H, and low pressure centers, marked by the big red L. And look, these aren't just random pretty colors. They represent two fundamentally different atmospheric states constantly battling it out for total dominance. One brings absolute calm, and the other, pure chaos.
Okay, so whenever you spot that giant blue H, I want you to immediately think stability. The blue H means we've got cool, sinking air. And because that air is literally pressing down on us, it acts like a massive, invisible lid that completely shuts down cloud formation. It's kind of like the atmosphere is just taking a deep, relaxing breath. This is what gives us those crisp, picture-perfect days, the stable weather that absolutely guarantees your weekend picnic is good to go.
But then we have the red L. This is where things get super energetic. If the blue H is a calm breath, the red L is the atmosphere basically throwing a tantrum. Instead of a sinking lid, we're dealing with warm, rising air. It gets shoved up into the sky where it cools, condenses, and, you guessed it, produces stormy weather. When you're looking at a red L, you are literally looking straight into the active engine of a brewing storm.
Moving right along to Section 2, tracking frontal boundaries and clashing air masses.
So, what happens when that cool, sinking air from a high smashes into the warm, rising air of a low? Well, they collide, and that collision creates a frontal boundary. Now, these aren't just static, boring lines drawn on a map. They are highly active, physical transitions moving between completely contrasting air masses. Because this is where the real action happens, the actual battlegrounds of our weather. Meteorologists map them using really specific, high-contrast icons so they immediately pop out at you.
If we put these mechanisms side by side, it's super easy to see the difference. We can perfectly contrast the sharp, almost aggressive nature of a cold front against the much more gradual, sweeping vibe of a warm front. Let's break down the specifics.
First up, the cold front. You'll recognize this boundary by the solid blue line covered in little blue triangles. And here's a pro tip. Think of those triangles as literal arrows. They point aggressively in the exact direction the cold front is plowing forward. When this sharp boundary bulldozes through, it creates a really abrupt shift. It's swift, it packs a punch, and it brings a rapid temperature drop, usually paired with sudden, heavy storms.
Now flip that, and let's look at the warm front. This one is marked by a solid red line with these rounded red semicircles. Instead of aggressively plowing underneath things like a cold front does, this warm air gently glides right over the top of the colder air mass. Because it's this gradual, sloping climb rather than a sharp wedge, the weather it brings is completely different. A warm front gives us steady, widespread drizzle. No sudden violent storms here, just a gloomy, rainy day.
All right, Section 3, from data to forecast, where we start synthesizing everything.
To actually turn all this raw data into a reliable prediction, forecasters follow a pretty strict sequence. Step 1, you analyze the surface analysis charts to find your high and low pressure centers, plus those frontal boundaries. Step 2, trace the movement vector. That's just a fancy way of saying you figure out the exact direction and speed a system is traveling. And finally, Step 3, you predict the impending conditions, stuff like temperature shifts or precipitation, for a specific location based on that movement.
Which brings us to Section 4, making weather predictions by animating the map. Let's actually run through a real-world scenario. Imagine you're staring at a static weather map right now. For Step 1, your eyes lock onto a red L sitting right in the middle of a region, and trailing down from it is a distinct solid blue line covered in blue triangles. Boom! You've just successfully isolated a low-pressure system and an advancing cold front.
Okay, Step 2. You look at those blue triangles, and you treat them like directional arrows to trace the movement vector. By doing this, you are literally animating the map in your head. You're taking it from a frozen, static image to a dynamic, moving system. You can practically watch that sharp line of blue triangles marching forward over time, pointing straight toward a specific city.
And now for the grand finale, the forecast. Because you know exactly what a line of blue triangles means, and you've tracked its vector. You know for sure this isn't bringing the calm of a blue H, and it definitely isn't the gentle drizzle of a warm front. You can predict with absolute confidence that sudden storms and a sharp temperature drop are about to hit that specific location. You just turned static data into a highly dynamic forecast.
So I want to leave you with a little challenge to test out your new meteorological chops. If a surface chart shows a red line with semicircles and it's tracing a movement vector directly toward your city, what exactly should you predict for tomorrow's weather? Keep these mechanisms in mind the next time you open up your favorite weather app or catch a static chart on the evening news. You've now got the tools to read the atmosphere for yourself. Thanks for hanging out with me on today's Explainer, and keep looking up.